On stage rocking, I'm stir crazy. Coco flow like 1980s. Come lit, still I drop lazy. None of that maybe. Energy, energy, energy.
Just vibe. Voting on 45, don't get out of line. Yeah. Ooh, 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 pick a side. Only double lines we cross is dollar signs. Yeah. Ooh, 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 hold up. Wait, I hear you just got paid, make it rain. Energy. She more Cancun, he more Central Pay. Big wave in the room, the crowd gon' move. Look around, everybody on mute. Look around, it's me and my crew. Big energy.
We was on stop mode, got froze from page Vogue, no pause, chat too much, bro, clip on load, that's that Kodak, energy, 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 yeah, yeah.
All right. Welcome back. Welcome back. We are talking about energy and spontaneity. Energy and spontaneity. Okay. Many spontaneous processes proceed with a decrease in energy, meaning as the process, at the start of the process, it's at higher energy, and as it proceeds, right, there's energy that's released. And I'm sure that right now what's screaming in your head is, oh, this must be exothermic, right? Many spontaneous processes are exothermic, right? We start at a higher energy and then energy is released. So we end up at a lower energy at the completion of the process. So because spontaneous processes proceed with the decrease in energy, they are often exothermic, but not always, right? All spontaneous processes are not exothermic, nor are all exothermic reactions necessarily spontaneous. So let's talk about an exception. So at room temperature and a pressure of 1 atmosphere, if we have solid water going to liquid water, our change in enthalpy is positive 6.01 kilojoules per mole. If we have liquid water going to solid, so notice the reverse reaction, then our change in enthalpy, it's the same magnitude, it's just switched in terms of our signs. So going from liquid to solid, the change in enthalpy is negative 6.01 kilojoules. So which is spontaneous? Which is spontaneous? Pause this video and think about it. So it turns out, right, that going from solid to liquid is spontaneous, even though this delta H is positive, which suggests that this is an endothermic reaction, right? This is an endothermic reaction. So here's an exception where an endothermic reaction is actually spontaneous as opposed to the reverse exothermic reaction. So thinking about that same example, going from solid to liquid, this is a chamber, right? These little circles in here represent gas particles. So if we have the valve closed here in such a way that all of the gas particles are in this left side of the chamber, and then we open it, what we will see happen spontaneously is a dispersal of energy. These gas molecules will disperse in such a way where there's an equal amount in both sides of the chamber, right? So similarly, or not similarly, I'm sorry, if we do reverse, right, going from this uniform dispersal or distribution to all of the gas molecules going into one side, that would be non-spontaneous. So it's similar in that previous example we looked at, right? Water going from solid to liquid, it is spontaneous for these molecules, right? So if you literally take out an ice particle, an ice cube, that's what I'm trying to say, and you just sit it on the kitchen table, right? You will see that it will eventually go to liquid, because this dispersal of molecules or particles, basically being able to move about freely, you can think, is a spontaneous process, right? So that's why going from solid to liquid, even though there's an energy input, it's still spontaneous. Similarly to if we have gas particles dispersing between two sides of this chamber. So let's say we have two particles, right? They can be two metals, just two particles that are at different temperatures. So X has a higher temperature than Y, right? So essentially it's hotter. Now, when we bring them together to touch, right, if they make contact, what we will see is this heat, right, that results in a higher temperature in X will disperse evenly, and it will go into Y until they reach thermal equilibrium, right, until they reach a uniform distribution of particles between the two. So the dispersal of energy is spontaneous, right? This is a factor other than energy that's important to the spontaneity of a process. So if we have more uniform dispersal of matter and energy, which we saw in both of these examples, they can be the driving force of a spontaneous process. More uniform dispersal of matter and energy can also be the driving force of a spontaneous process. And this introduces a thermodynamic property called entropy. So entropy this is basically what we're talking about. What we're witnessing in action in these two examples is something called entropy, which we will transition into in the next video.